大家好，我是 COSCUP 暨 RubyConf 2021 Day One 下午场的 RB105主持人 Snowmint， 非常高兴能够以线上的方式跟大家一起参与这次的年会。接下来的议程是从1点至2点整，此议程以英文进行。This meeting will run from 1 p.m. to 2 p.m. Now let's welcome our speaker, Dan Guanxing. He's going to share with us about the topic of exploring your Apple M1 devices with open source tools. Now please join me in welcoming our speaker, Dan Guanxing.
Hi, I'm Guanxing Dan. The title of my talk is Exploring Your Apple M1 Devices with Open Source Tools. I'm gonna tell you a little bit about how to know more about your M1 devices with open source tools. As you might guess from the title, this talk is for novice programmers who didn't know that although Apple doesn't tell you some information, you can use open source tools to retrieve them. I'll review an example I talked before, and then use 3 more little examples to show you how we could get more information with open source tools. Hopefully, you could get inspired to retrieve more information from your devices. Okay, who I am a software guy. I learned to use open source software before the term open source was coined. I learned to use Unix and open source software on Lexi 780 running Potash 3 BSD. I also learned some Mac in the early 1990s. I became a Mac user when Apple switched to Unix OS Mac with the MacOS 10 in 2001, I think. And recently, I worked on new network performance related topics on edge devices. So I contributed from time to time to TensorFlow, especially the TensorFlow Lite part. I have another talk on the MLPerf mobile app, which is a performance benchmark application this year. Okay, yes, macOS is mostly proprietary software. However, Apple does use open source and it just released some source code with open source licenses. For example, the XMU or say the Mac kernel. In case you don't know it, the macOS 10's kernel is Mac-based. Its source code is open source. Usually, newer source code the macOS kernel is released with BSD license a couple months later after a specific version of macOS is released. And the framework part of IOKit, which is Apple's framework for writing kernel extensions, is open source. We'll talk more about the IOKit later. Finally, Mac OS is Unix in terms of standard conformance. So most Unix-related code is expected to work on Mac OS. I'm interested in knowing more about devices I am using. I talked about the iPhone thermal-related software and hardware in COSCUP 2 years ago. I want to learn more about how iPhones work. I found that M1 plus macOS is useful. Software for M1 is closer to A14 plus iPhone OS than software on Intel platform, which means understanding M1 plus macOS helps understand A14 plus iPhone OS. And as you might know, macOS is fundamentally more hackable than iOS. There is no need to jailbreak. There are more useful tools. For the example, the powerful DTrace. And there are more symbols in kernel and kernel extensions. And there is a kernel debug kit, the KDK, which contains more robust debug symbols of X and U. Previously, I was able to collect temperature-related information on iOS devices. So you can see there are more and more temperature sensors in iPhones. Alright, how does the little program work? First, you might wonder why we cannot find apps with this kind of information from Apple's App Store. Is jailbreak required? No, jailbreak is not required, but a somewhat undocumented framework is used. So don't try to submit it to App Store. Mostly, it will be rejected for iOS platform. What is undocumented? It's the IOKit part. The IOKit is a public and well documented on macOS, but not on iOS. I'll talk more about this later. We use Apple's HID class of IOKit to retrieve information. If you have a look at the source code, Objective-C is used to get sensor information using the IOKit framework. Swift, I wanted to learn more about the Swift at that time. That's why it was used. As I said, IOKit is public and well documented on macOS. It's a driver or say kernel extension framework covering both user and the kernel space. In case you don't know anything about the IOKit, you might find a lot of information from Apple's website, and there are some books. For example, one of my favorite macOS 10 book, the macOS 10 internals systems approach, had explained and illustrated IOKit. IOKit is derived from next steps driver kit, which was written in Objective-C. Apple chose to rewrite it in C++, and of course, it's a subset of C++, and the code is IOKit. As you might know, in WWDC 2019, Apple brought the name driver kit back to macOS. However, although it's relatively well documented, not all information we need are documented. Fortunately, I'm old enough to know an old saying in open source community, which is use the source look. HID class. We use IOKit's HID class to read the values of thermal sensors. Here, HID stands for Human Interface Device. As far as I know, IOKit's HID class is originally designed for USB HID devices. But as you can see, now its usage is far beyond USB. So there is USB usage page to describe non-USB usage. And there is an IOKit command line tool called IORegistry, which we can use to retrieve IOKit registries, or say to enumerate IOKit devices. This is originally what I used to find thermal sensors. The following is a part of the output of IOHIDE-L. As we can see below, there are primary usage equals 5, and the primary usage page equals to 60 by 1000 and 280. And the device usage pairs equal to its device usage page and the device usage. If you get a clone the source code, my little program from GitHub, and try to build it for iOS devices, you will find an error message saying IOKit related headers cannot be found. Because, as I said, IOKit is not a public framework of iOS. You have to get those header files from other places. If you don't know how to do it, borrowing those header files from the macOS SDK should work. There are non-public data types and functions. For example, I found the device usage pairs for thermal sensors from previous versions of IOKit related source code opened by Apple. And the IOHIDeventSystemClientCreate function, which I learned from the iPhone DEV wiki, is not a public one, so there is no function prototype for it in standard IOKit headers. Finally, I also found that on iOS devices, the plist file or the files in system library thermal monitor is interesting. Okay, ghidra. To check binaries on macOS or iOS, reverse engineering tools usually are useful. Here we use ghidra. Ghidra is an NSX reverse engineering tool which is open sourced in 2019 with Apache license. It's mainly written in Java and C++, and the plugins for ghidra could be developed in either Java or Python. The IOHIDeventSystemClientCreate function is a function that we used to create a handle. Then we can use the handle to retrieve information from IOKit HIDClass. I learned to use the IOHIDeventSystemClientCreate function from the iPhone DEV wiki. Currently, there is no function prototype for IOHIDeventSystemClient in the HID system IOHIDeventsystemclient.h of standard IOKit headers. But there is IOHIDeventsystemClientCreate simple client, which is not what we want. Why? With the help of ghidra, we can find that they are different. One is to call the IOHIDEventSystemClientCreate with type function with type 3. The other is with type 4. They are not the same. Property list. Property list files in system library thermal monitor are interesting. Here is one of the files we can find in iPhone 12 file system. As we can see, there are some information. There are sensors, control loops, and others, such as decision tree tables. For sensors, in the P list, their names are in 4cc, the 4-character code, which are quite different from what we get from HIDClass. More about the little program and the thermal-related stuff on iOS devices. If you are interested in knowing more about the little program and the thermal-related stuff on iOS devices, you can check the slide deck of my previous talk. For MacOS devices, I converted my code to use a command line interface, which is supposed to be more Unix-friendly. I also converted my other code to use Objective-C classes from the Foundation framework instead of C data types of the core Foundation framework. Is there any other way to access thermal sensors? The short answer is yes. At least I know we can talk to Apple SMC sensor dispatcher to get some information. The good thing is that we don't need undocumented functions to talk to Apple SMC sensor dispatcher. All we need are standard documented IOKit functions. Those functions we are gonna use are IO masked port, IO service matching, IO service get matching service, IO service open, IO connect call scalar method, IO connect call structure method. For these functions, you can find the information from Apple's documentation or books. Yeah, there are some books on IOKit, as I mentioned. However, we still need to figure out, well, somehow magically or mostly by reverse engineering, what are the parameters to pass. For example, for the IO connect call structure method, only the first parameter, the connection, is trivial. We need to figure out what other parameters to use. And for this thermal sensor purpose and the other sensors, maybe we also need a special entitlement to access Apple SMC sensor dispatcher. The dispatcher method. When we call IO connect call scalar method or IOConnect construct method in user space. A corresponding kernel space dispatcher is invoked. It's similar to older Unix IO control. This is also a documented feature of IOKit OS driver kit. It's a virtual function called external method, which is to be overwritten by those who implement IOKit drivers. For this one, the dispatcher is Apple SMC kernel extensions, Apple SMC sensor dispatcher user client external method. And this method, if we decompile or disassemble it, we can find that it relies on a table at Apple SMC sensor dispatch user client underline method to choose which method to invoke. Kernel space method we can call. When we somehow decode the Apple SMC sensor dispatch user client underline method table we mentioned, we can find the dispatcher could handle 7 different methods. We'll use the first 3 of them to get some SMC sensor data. First, we use sget SMC sensor count to query the number of sensors we can get. Second, we can get 4cc names of those sensors with sget SMC sensor 4cc. Then we can retrieve sensor values with sget SMC sensor data. How to choose those methods? Usually the second argument of IO connected call scalar method or IO connected call struct method, the selector argument is used to select the method to call. So what does this little program get? What do we get on an M1 MacBook Pro with this little program? We can find that we can get a hexadecimal C or say 12 sensors on this MacBook Pro. Then I got 4cc names of them. Then I got the values of them. And I spent some time so that we can map most of the sensors name, 4cc names to more meaningful names we got previously. Okay, enough thermal sensor information. We have more examples to tell you what we can get on M1 devices. Cache information is an interesting topic. Apple didn't publicly disclose cache configurations of A14 and before. Yes, Apple did reveal M1's configurations in its November 2021 event, but from software side for iPhone and M1 before macOS 12 and iOS 15, there are no such information we can retrieve from either macOS or iOS. Because, first, information are not input the message. Second, syscontrol doesn't work as expected. Information of the first booting code was used. You cannot see other codes information. Third, they are P and E cluster in modern Apple SoC. We'll back to what those P and E are later. However, I managed to get the cache information from device tree. Unfortunately, there are new syscontrol entries in iOS 15 and macOS 12. For those who don't know it, modern mobile SoCs consist of cores using the same instruction set architecture, but implemented with different microarchitectures. Those cores deliver different performance and have different power characteristics. Called this big little because there were two clusters of cores. The bigger cluster was for performance, and the little cluster was for energy efficiency. Nowadays, on flagship cell phones, there may be more different kind of cores in the same cluster. Apple doesn't use the term big little. On A14 and M1, there are big and little cores, but they are called P and E cores respectively. Test 1, 2, 3, 1, 2, 3. Okay, let's see some real examples of cache information reported by syscontrol. What I am showing on the left-hand side are part of the result I got when running syscontrol on an M1 MacBook Pro. You can see cache information match efficiency codes information provided by Apple. On the right-hand side are information from an iPhone 11 Pro running iOS 15 beta. You can see there are perf level 0 and perf level 1. How do I find those symbols? ODNM could traverse the symbol table of an executable file and find those names. Oh, that's not so old because the NM on macOS is from LLVM, which could be relatively young. Perf level related code appears at several places in new kernel binaries, but we cannot find them in older source code or binaries. Okay, how ghidra can help. With syscontrol mib init in new kernel binaries disassembled and decompiled, we can find that in newer macOS or iOS kernel binaries, unlike in older binaries, there is perf level related code in the syscontrol mib init. Okay, more perf level related code. As I mentioned, there are more perf level related code at some places in newer kernel binary, such as ML, CPU, get, info type, and others. Syscontrol hardware generic. Syscontrol hardware generic is the function you should check if you are interested in learning more about syscontrol stuff. But it's too long to be listed and discussed here. So we just leave this as a reminder. IOReport. The other days, I need to read some of the information reported by powertrics. I think I could not find some of the information elsewhere, but I don't want to keep invoking powertrics because the powertrics must be invoked as a superuser. It turned out that I have to use IO reporting functions to retrieve data from kernel-side IOKit modules. Unfortunately, I cannot find the documentation on using IOReport in user-level program. Fortunately, there are kernel-side code comments and some user space source code, which is open sourced by Apple. With them and some previous work, I put together an example that could dump all the IO reporting information it could access. Let's discuss what are the information from powertrics you or I might need. And let's use CPU as an example. CPU-related control on iOS devices and macOS M1 devices are quite different from x86 ones. There is no ACPI, and Apple doesn't use either PSCI or SCMI. And some of you might be familiar with CPU-related control in Linux kernel, so we use Linux, some Linux terms here. First, the CPU hub on macOS. The old Bach processor exit system code used to work on jailbroken iOS devices, but it doesn't work on M1. For CPU freak, there is no way to retrieve current running frequency of CPU on iOS devices. And there is no public document on how its DVFS works. And yeah, the peak frequency is relatively easy to detect. You can write a group of assembly codes, then you can detect it. And for CPU scheduling, yes, there is some scheduling code in open source XNU code, but it seems far from complete. powertrics does provide some of the CPU information. That's why we need it. Here are some of the CPU-related information reported by powertrics. How to get and where to find IOReport information. Since IO reporting is an IOKit mechanism, we can see that maybe there are some information from IO registry-L. And we can also do something similar to what we had done, which is to use the source. From XNU kernel source code, we can find what IO reporting is and how the terms, channels, and legends are used in IO reporting. With that, we know how to interpret the IOHIDE output to some extent. Here are some of the output from my little program reporting some CPU-related information. How the little program works. It's quite simple. Actually, it's less than 100 lines of code. The steps are first, select the IO reporting channels with IOReport copy channels in group or IOReport copy all channels. Second, subscribe to selected channels with IOReport create subscription. Third, get samples with IOReport create samples. Then we can use IOReport iterator to iterate through all the samples. And there are other utility functions. The example I want to talk is Apple Neural Engine related. Apple said in the M1 event that provides machine learning acceleration on CPU, GPU, and the neural engine. You might wonder, how can you be sure that your fancy neural network models are fully accelerated by neural engine? As far as I can tell, the answer is that you cannot if you only use a public API provided by Apple. With public API in coreml framework, the option ML compute units O is to allow your model to use neural engine. You don't know which layers of your model are actually running on neural engine. Fortunately, the famous hacker geohot dug out a lot of details of ANE when he tried to use ANE for his deep learning framework TinyGrade. How he did that? You can find that he spent tens of hours hacking with broader system knowledge and open source tools. Said geohot worked out many useful information of the ANE. Those details may take a couple hours to go through. Here, I just want to highlight that if some layers of your neural network model could be accelerated by the neural engine, those layers are converted or, say, compiled into a HWX file, which is an undocumented MacOS file with proprietary OPs. If you want to know more about those details, I suggest reading ANE-related code in TinyGrade or watching Jihad's hacking videos on Twitch or YouTube. The information on the right-hand side of previous slide is actually summarized from this big table by geohot. Based on geohot's description and the programs, I drew this with LaTeX. Simplified view of how an app could use the coreml framework to use the neural engine is like this. There is a daemon called ANE compiler service, which is responsible for converting files in compiled coreml model C directory into a HWX file, which we mentioned in previous page. And there is another daemon, ANED, which is in charge of other command and control. When you use coreml framework, the framework uses XPC, Apple's IPC mechanism to talk to the two daemons. The two daemons consequently talk to a kernel extension called the Apple H11 ANE interface via the IOKit we mentioned. Okay, external method or say dispatcher again. With ghidra, we can find that for ANE, the main dispatcher for user level client is the H11 ANE in user client external method. And we can find in the table of method used by the external method is quite big. There are underline ANE, underline device open, underline ANE, underline device close, underline ANE, underline get status, etc. For your convenience, I put those methods into a table. You can see that there are more than 30 methods in this table, and various functions are provided by this dispatcher. There are device-related functions to open or close the device. There are status check functions. There are register rewrite functions. There are power-related functions to power on, power off the device to check if power is on or not. There are program-related functions to create program, to prepare program, to send request, etc. And there are firmware-related functions to load a function, to set the boot argument for the firmware, etc. How do we trace or figure out all the details of those functions? We can use the powerful DTrace. DTrace has probes for most of the methods or functions we listed. Not all of them though. For example, there is no probe for H11 ANE in user client underline ANE underline power on function. But mostly this is not a problem. Why no probes for some functions may not be a problem? For example, we mentioned that there is no DTrace probe for this H11 ANE in user client underline ANE power on function. But if we disassemble it, it's clear that we can trace this ANE power on, which has a DTrace probe instead of the underline ANE power on. A quick example of using device open and power on probes. Here in foo.d, I enable the underline ANE device open and the ANE power on and run it. Then in another terminal, I launched a program to run a coreml model which can be run
on Apple Neural Engine. Then I can see the 3 probes work.
If you follow the geohot's work, it seems something like a tool that can convert coreml model to ANE's HWX file isn't there. Thus, based on geohot's work, I wrote a little program that could convert a .ml model to a .hwx file and generate the related file, of course. Let's use the MobileNet v2.ml model hosted by Apple as an example. If you examine generated files, you can see model.hwx, which is the main MacOS binary file we mentioned. And there is a model.hwx.h13_perf_o.csv, yes, CSV file, comma separated vector. And it's a player profiling of the model. I think that's simulated result, not real profiling result. Okay. And there are dot file. As you may know, those are graph.vis format. Yeah. And last but not least, there are some immediate files. For example, in the espresso IR dump directory, there is a net_aux.json file which lists unsupported layers or say apps. And you can find that the latest layer of MobileNet v2, which is softmax layer, is not supported.
Recap. We introduced why M1 device running macOS is a useful platform. Then we give 3 examples of exploring a M1 device with open source tools. The first is to get cache information with syscontrol by name. The second is to retrieve IOReport information so that we can get information like what we can get from powertrics programmably. The third is to get ANEHWX related information, including examining which layers could be run on ANE. With that, we conclude my talk. Okay, that's it. We can start the Q&A session, or we can continue to share an example that you can use as a starting point to get more information from your M1 devices. The exercise is to get more CPU-related information from kernel extension on M1 devices. As we mentioned, not all of the CPU-related information is available in XNU source code. So where to find what we want? There are some kernel extension called Apple-COPCV star. For M1, what we want to check is conf.apple.driver.apple T8103 COPCV3. Here, COPC may stand for closed loop performance control. Well, I Googled it. Okay. And there are some CPU and GPU and others related information in Apple P8103 CLPCV3.kernel extension, which is a kernel extension used by M1 MacBook Pro. The goal of this exercise is to find the dispatcher in the kernel extension and write a user-level program to retrieve information.
Okay, thank you, Dan Guanxing. Thanks for your informative sharing. Now we are going to have the Q&A session, and we will now open the floor to the audience. Please feel free to ask questions, and I will show the Slido question list on my share screen. Let's welcome Dan Guanxing.
Hi. So the question is that, well, is there any legal issue for leveraging those non-public APIs? I think no, but you cannot. You are not supposed to use those non-public API and submit your code to Apple's either iPhone App Store or macOS Store. If you use them, then your app are likely to get rejected. That's what I know. People has been used this kind of non-public API and also undocumented API for a long time. I have never heard any kind of legal issue that you just cannot create a app and submit them to Apple's App Store. That's it.
Okay, did anyone want to ask any questions? You can also use YouTube to just leave a comment and ask questions. Or did speaker have anything can share or about this topic?
I think that's what I have now, for now.
Okay. Let's waiting for another people there who want to ask questions. This meeting will end at 2 p.m. Did anyone have questions?
If there is no questions, I think we can end this earlier. Or I just want to remind that we traditionally we can as far as I know, you let me think about it. As far as I can tell, people has been doing all kind of reverse engineering and reverse engineering on your own device. I think it's well, I don't think there is any legal issue. Even if you say publish some of your result. And as you might know that you can use a lot of open source tools and find a lot of open source information from Apple's on say opensource.apple.com. You might find those kind of information interest. Okay, I think we can, if there is no further questions, we can end this session earlier.
Okay, let's end this meeting earlier. And let's take a short break right now. The next session will start at 10:02. Thank you. 接下来进入为期15分钟的中场休息时间，感谢讲者以及大家的参与。下一场议程将在2点10分开始，谢谢大家。